In this second part of our projectile motion portion of the kinematics unit, we're going to take a focused examination of the foundation underlying two-dimensional motion of a projectile. And so when we consider two-dimensional motion, of course, we consider both the vertical and the horizontal components. And either way, we always take g to be a value of 9.8 meters per second squared. Once again, we do not add the negative value here because g refers to just the absolute value, as the equations of constant acceleration already factor in the direction of the acceleration vector due to gravity. So when we talk about a projectile, when we think about a projectile, we refer to an object that does not have an external contact with any other object or surface. But keep in mind, this does not apply to airplanes or birds. These have what's called thrust and lift, as we'll define on the next slide. So the objects in our examination will only have one external force acting on that one object, and that's the force of attraction between this object and the second, much larger object being the Earth. So this object in question here on the slide will have a certain quantity of matter that defines its mass, but because of that force of attraction with the larger object being the Earth, it will have a weight, and weight is a vector quantity which is reflected by the force of gravity specific to this unique object. And so we consider Newton's law of gravitation when examining both the vertical and horizontal components. As you'll see, it will only be applicable to the vertical component. And so we assume there are no other forces acting on the object. Now this is starkly different than, for example, an airplane. So when we talk about an airplane, as defined in the previous slide, airplanes have thrust and lift. So we know the first external force acting on this airplane is that force of attraction between the airplane and the much larger object being the Earth. Now this airplane, having a considerable mass, will also have a very large weight that is always directed towards the other object, and in this case it will always be directed vertically in the negative direction towards the Earth. Now the airplane, if this was the only force acting on the airplane would follow this vertical path and move towards the Earth, but we know it doesn't. And that's because there is another force that is actually pushing and holding the plane in the air to counteract the weight of the airplane, and that's what we call lift. So the lift force comes from, in part, the force of the air that opposes the forward motion of the airplane. So as this airplane moves through a fluid environment, and that fluid environment is the air, and that air is made up of molecules that slams up against the airplane and applies a force in the opposite direction. Sometimes that's referred to as the drag force of a fluid, be it a liquid or a gas. In this case, it's air molecules that opposes the forward movement of the plane, but this will be proportional to the force acting in the opposite direction, and that's what's called the thrust force. And the airplane has these very large engines which consumes airplane fuel, and that drives turbines which pulls air in the front, forces that air at a very high velocity out the back, and the air molecules will then push back against the plane, giving it that thrust, pushing it forward, which will be opposed by the air molecules, and these air molecules will spread over the top and bottom part of the plane, and it's that pressure generated by these air molecules moving along the underside of the plane and the wings that gives that airplane lift. But we will focus on the projectiles that are not subject to any other force than that of the force of gravity. And we're going to take an isolated example of the shot put performance. So on this slide, we see two of the world's best shot putters, Michelle Carter of the United States and Valerie Adams of New Zealand. And once again, we review the key factors that will determine the kinematics of the projectile. And those key factors relate to the height of the release, which we'll define on the next slide, the angle of the release of the object, and the velocity of the release. And we'll just make a note at this point. We'll address this a little bit later on in this projectile motions subunit of Module 3. That Michelle Carter is reported to have a standing height of 5'9". Valerie Adams is 6'4", and these two facts will be factors in the release height as we examine it much later. So when we examine the kinematics of the shot, we always start with our frame of reference, and as usual, horizontal motions to the right are taken as positive. Vertical motions up are taken as positive in respective X and Y directions. So at the instant that the shot breaks hand contact with the shot putters, it becomes a projectile, and it will have a velocity, an initial velocity vector at this particular having this particular projection. Now we can take this initial velocity vector and decompose it into both horizontal and vertical components. And this is important to know because the shot will take what's called a parabolic path or a parabolic flight, which is characterized by an apex, which is the most vertical, the most maximum vertical position, and the lead up to the vertical position, maximal vertical position to the apex, will mirror the trajectory on the opposite side in terms of its shape. So remember that the initial velocity is going to be referred to as the takeoff velocity. That's the point that the object in question breaks contact with an external surface or an external object. So in the shot put, we'll refer to this as the release velocity. So the terms takeoff and release can be used and are used interchangeably. And these are terms that are used to describe the initial velocity as soon as the object becomes a projectile. One last point to make on this slide is up in the top right-hand corner. Note that this particular shot put takes a much more vertical trajectory than the one we started with here. And so the object can take on different paths, as the one in the top right-hand corner takes on a more vertical orientation. The shot put at the bottom of the slide takes on a more horizontal trajectory. Although these paths appear different, they do share one thing in common, is that they are all described as having parabolic parabolic flight. And going back to the shot put here, we'll take a look at the pattern of the path of the shot put released by Michelle Carter. Once again, don't forget about our frame of reference. We always start with our frame of reference. And to answer the question, is vertical and horizontal velocity different? The answer to that question is yes, and we'll take a look at that here in a moment. So we know at the instant that this shot put is releasing from Michelle Carter's hands, and so we assume at this point it's breaking hand contact. That shot put will have an initial vector defined by its magnitude through its length and the angle from the horizon, which means that we can decompose this vector into an initial x component and an initial y component, which can be computed using the equations on the top right-hand corner of this slide. So we see that in order to calculate the x velocity or the x component to the resultant velocity, it's going to be a function of the magnitude of that initial velocity times the cosine of the angle from the horizon. Likewise, to compute the y component, once again, it's the same magnitude of the resultant velocity, but it's going to be a function of the sine of that angle from the horizon. And there's our release angle. So once again, we have a parabolic path, which is defined by an apex, or the point of maximum height. Now, notice that the release point and the point of landing are going to be different. These 2 points, despite being different, will not have any influence on the parabolic path of that shot put. The only difference is the start point and the end point. And the difference in those 2 points is what we define as the height of release, which will have an influence on where it lands, but it will not have an influence on the parabolic nature of this path. And so if we select another point in this path, the instantaneous, so the velocity of the shot put at this point in the path can be defined as a vector, and these velocity vectors are tangent to this path, which means they cut at a right angle if we imagine this point was a circle. Of course, it's not a circle. And this velocity, this resultant velocity, can be decomposed into an x component and as a y component. And if we focus on the velocity of the shot put at the apex, we see that the vertical component is no longer visible. The length of this vertical vector collapses to 0 at the apex, so that the only velocity that the shot put is taking at this instant in its path is a horizontal velocity. But we know at the apex, the vertical velocity has to transition from a decreasing positive value through 0 and into an increasing negative value. And we see that at this point in the path of the shot put, where the vector is defined by a length, which can be decomposed into both y and x components. And as it continues to travel and we isolate a different point, we see that the length of this vector is going to be the same length as the initial vector, because we picked a point that is at the same vertical spot as the release velocity, except that it's pointing in the opposite direction. And so it's going to be defined by a horizontal component and a vertical component. And if we continue to follow the path of this shot a little bit later on here, we see that the resultant velocity vector is longer than it was at this previous point. And once again, we can decompose it into horizontal and into final vertical components. Of course, this would not represent the final point. The final point would be at the very point right before it makes ground contact, but these vectors would be off the PowerPoint slide. So the final point is actually a point right at the very instant before the molecules of the shot put contact the molecules of the ground. So a couple of things to note here is that in terms of the horizontal velocity vector, it's constant. So we see that the length of the vector in both its direction but particularly its magnitude does not change throughout the entire path. That length is going to be a constant because it's not influenced by gravity. It could potentially be influenced by air resistance if there's a very strong headwind, but we're not going to consider that in our examination here. And that the vertical velocity vector, we see its greatest at the point of release, and it starts to decrease to where it collapses to the zero vector, where it transitions to a direction pointing downward. And as long as that shot put is in the air and it's a projectile, that vertical vector will continue to lengthen. And so this ends the second part of our projectile motions subunit of Module